All right, let's talk about organic chemistry. But for a minute, let's forget the dry textbook diagrams and all the complicated jargon. Instead, we're going to look at these complex reactions in a whole new way, as a kind of molecular dance.
I know. It might sound a little out there. Molecules, dancing, but seriously, just stick with me on this, because once you start to see it this way, a whole lot of really complicated chemistry is going to suddenly make perfect sense.
So let's just set the scene. The dance floor, that's our reaction. The dancers themselves, well, those are the molecules. The way they hold hands, those are the chemical bonds. And the reactions, those are the actual dance moves. It really all just comes down to who's dancing with whom, and when they decide to switch partners or even leave the floor altogether.
Okay, so let's get into it. The first and probably the most common move you're going to see on this molecular dance floor is the good old partner swap. In the world of chemistry, we call this a substitution reaction. And it's pretty much exactly what it sounds like. One dancer, an atom, or maybe a whole group of them, gets tapped on the shoulder, and another one cuts in. The really important thing to notice here is that the main dance formation, the carbon backbone, stays completely intact. It's just a clean, simple, one-for-one swap.
Let's watch this move in action. So we start with our ethanol molecule out on the floor. Then along comes hydrobromic acid. The bromine ion is our new dancer, and it sees an opening. It swoops in, taps the OH group, and that OH group is gracefully escorted off the floor. The end result? A brand new partnership is formed, and now we have bromoethane, a perfect molecular partner swap.
But hey, dancing isn't always about just swapping partners, right? Sometimes a pair of dancers just decides to leave the floor together. And that brings us to our second big move, the elimination reaction.
Now, this is totally different from what we just saw. Instead of a one-in, one-out kind of deal, we're actually losing two groups from neighboring carbon atoms. Imagine two dancers standing next to each other in a line dance, and both of them just leave. This leaves the two carbon atoms they were attached to with, free hands. So what do? They link up, forming a new, much stronger double bond between them.
Let's go back to our same ethanol molecule. We start with the same dancer, but this time we turn up the heat and add a catalyst. And wow, the outcome is completely different. There's no partner swap. Instead, a hydrogen atom from one carbon and the OH group from the carbon right next door, they leave the dance floor together. This frees up those two carbons to form that new double bond, and just like that, we've created ethene.
Okay, but this is where it starts to get really interesting. What happens on a bigger, more crowded dance floor? A more complex molecule might actually have a choice about where it forms that double bond. So, how does it decide? Is there a rule?
Oh, you bet there's a rule. It's called Saytzeff's Rule, and it basically says that nature plays favorites. The reaction will almost always favor forming the most stable double bond possible. And what makes it stable? Being surrounded and supported by other groups. You can see it right here in this chart. The major product, the one that forms most of the time, is the more crowded, more stable one. Just like dancers, molecules prefer the most balanced and supported formation.
All right, so we've got the main dance moves down, substitution and elimination. But how exactly are these moves performed? Let's zoom back in on substitution for a second. Turns out that partner swap can happen in two very distinct styles, a super fast one-step or a more patient two-step. So let's compare them. Over here we have the ZnCl₂ mechanism. This one is all about speed and timing. It's a single, swift action where the new partner arrives at the exact same moment the old one leaves. And then you have ZN₁. This is a two-step process. Here, the old partner leaves first, creating this little moment of drama before the new partner finally steps in. Let's break down each of these styles.
First up, the ZN₂ mechanism. I want you to think of this as the tango of chemical reactions. It's fast, it's precise, and everything happens in one perfectly coordinated motion.
And this is the key. There is no waiting around. The new dancer, our nucleophile, which is just a fancy word for a group looking for a positive charge, attacks from one side. At the exact same moment, the old group leaves from the opposite side. This backside attack works best on a less crowded carbon, where there's plenty of room to maneuver. It's a simultaneous, beautifully efficient exchange.
Now for the complete opposite style, the ZN₁. If ZN₂ was a fast tango, this is more like a slow dance, with a long, dramatic pause right in the middle. It's basically a two-act play. So in Act 1, and this is the slow part, the leaving group just leaves, all on its own. It creates this unstable, positively charged thing called a carbocation intermediate. It's like a dancer left all alone in the spotlight.
This is more likely to happen on a crowded carbon because all the neighboring groups help stabilize that lonely positive charge. Then Act 2 happens super fast. A new partner sees the opening and quickly swoops in to bond with that waiting carbocation, and the dance is complete.
So we've learned the moves, and we've learned the styles. Now I think it's time we meet some of the star dancers, don't you? Let's put a spotlight on a few well-known compounds and see how they perform on the chemical dance floor.
First up, let's give a round of applause for chloroform. This molecule is a really versatile dancer, known for participating in some very specific and important reactions.
Chloroform has a couple of signature moves. In the carbylamine reaction, it dances with primary amines to produce a really distinct, unpleasant smell, which is actually a great way to identify them in the lab. Then there's its more elegant move, the Reamer-Timon reaction. Here, it partners with phenol to create salicylaldehyde, a key component in all sorts of fragrances and flavorings.
And let's not forget carbon tetrachloride. Its role is a little bit different. It's not so much a dancer itself. It's more like the dance floor manager. You see, it's often used as a solvent to control the environment of the reaction, making sure the main dancers can perform their moves correctly without things getting out of hand.
So there you have it. By seeing chemistry as a dance, we've unlocked the secrets of its core moves. We've seen molecules switch partners and leave the floor, and we've seen them do it in different styles, from the swift tango of SN2 to the patient two-step of SN1. But this just opens up a new question, doesn't it? We've seen all the dance moves, but what decides the tempo of the music? What controls the speed of this molecular dance? Well, that's a fascinating question for another time.